Hello, good morning. I'm José Proença, and I'm here to talk to you about ARCS, which is a reactive programming language for synchronous connectors. And this presentation will be shared with Guilhermina Cledu, who will give the second part of this presentation. So all the tools that we made are available online on arcatools.org/sharp-arcs. So if you want, you can try the tool by yourself during this talk as well, or you can also download it and compile in your own computer. So everything is done in Scala that's compiled into JavaScript. So to guide you through the rest of this presentation, we will start by providing syntax. So how to define programs that are visualized in this architectural layout in this part. And I'll also explain some motivation. So how does ARC sit between reactive languages and synchronous languages? And in the second part of this presentation, Guilhermina will talk about the semantics of arcs. So roughly speaking, it includes some basic set of constructors which are based on Rio, including some primitive connectors and some plugging. And they also include some special variables, these reactive variables that are denoted with this till. And we also provide some support for algebraic data types. But I'll introduce this very slowly using a hands-on demo. So here on the side, you can see what you first see once you open the website. I'm going to delete this, and I'm going to just show you the FIFO connector. So if I write FIFO-A, and I press here or Shift Enter, it draws the FIFO with a single input port, which is port A. And in this case, this expression outputs a single port, a single stream of values, which is outside this return port. Instead of the FIFO, I can also write something like this: the lossy. The lossy in Rio is a channel or a connector that might lose data when it's being passing from A to B, or even a drain, but in this case, the drain has two input ports. I'll write A and B. And in this case, it just gets both data. So how do I combine things? Well, if I have a FIFO and I want to put in parallel with the lossy, as you saw before, I can write things like this. So a FIFO and a lossy, both of them with a different input and both of them output in a different port. I can also say, no, this FIFO will output to B, and B is exactly the one being used by lossy. So this will accomplish sequential composition. So the results of the FIFO going to B that go into the lossy. Other thing you can also see is that this is not outputting anything anymore. The only output of this program is the result of this lossy, which is this port. So if you want to combine, them by merging the results, so both the FIFO and the lossy you output into a port, then I can do like this. And in this case, there'll be a port C, which is black because it's not the result of the program, but is merging the results from both operations. I can write a C in the end, enter, and then I'll make it an output as well. The same way I have this merging behavior, I can also describe the replicating behavior. So if I just write both of them starting from the same one, and let's say this goes to B and this goes to C, and then I want to output both B and C. Spaces or enters are the same here. So now you have this replicating behavior. The same port A is applied to FIFO and the lossy. So these are the basic constructs in order to generate this. So continuing this presentation, let's talk about more the motivation. What are synchronous connectors and what they mean in arcs? So this program that I already saw before, written by this, means that A and B are values that might arrive and they are consumed by this program, which means that they will go straight to this barrier, which is the same as this drain that you saw before, guarantee that they have to go together. This FIFO buffer will get and consume the same value that goes to the barrier, and will block further incomes until it gets empty. This will merge the behavior of A and B, but in the sense that we will either choose the value from A or from B before outputting it. I call synchronous here because it might impose things to come at the same time and blocking otherwise, or might block something from occurring, this one from being fired, that will propagate and also block that one from being fired. Continuing and now look a bit into reactive programs. If you look at this example, that's a typical example to illustrate what's the purpose of reactive programs, quite often presented as libraries for existing programming languages. In here, you multiply A by B, and the result we add to the value of A. In this scenario, these are reactive variables in the sense that they might be updated. And once they're updated, I want to run all the rest of the computations. In this case, this times operation is triggered if this is updated once. But this plus is not triggered if C is updated alone. It's triggered if both C and A are updated. So it waits for both of the updates. This is to avoid what they call the glitch problem, which is when you perform an operation by a trigger without waiting for all the inputs that are dependent on the same A. And there are several solutions in literature to handle these kind of situations. If you look at other different kind of reactive program, in this case, about how do you model a graphical user interface where you want to use a Boolean reactive variable to select if you want to display a time stream or the mouse coordinates stream. So these, on one hand, you see already there are different kind of streams, the ones that are constantly updated, quite often known in literature as continuous behavior, and these that are sometimes updated, often referred to as events or signals. And you also see here a different kind of characteristic, which is the notion of dynamic dependencies, because the result of the display will depend either on this one or on this stream, not necessarily on both streams. Other thing you also want to see is that it might be also the display that says, I want a new value, since they are always up to date, and you might be the one selecting or choosing the refresh rate when you want to have the new value. If you try to model in our system in args, you first grab this select, which you treat as a variable, a value that you consume, and first you put it inside a reactive variable, which is stored and might be read multiple times. And then you use this match to be able to deconstruct it to see if it's either true or false. I use the word deconstruct because this is actually only works if you define first this Boolean data type that's actually used by this selector. So it provides some way of adding algebraic data types that might be parameterized and be able to construct or destruct elements within our language. So this is the wrap up for the first part on how to define. On the second part, we'll have Guillermina talking about the semantics that will give the interpretation of these args programs. So, Guillermina.
Good morning, I'm Guillermina Cledu, and I'm going to talk more about the semantics of args programs. Here we have the alternator example from before, and we can specify this by composing simpler constructs in our DSA. And we have some input streams like A and B, and we have output streams like X. And although not explicit here, we have also memory streams, which for now they are provided by primitive constructs like the FIFO that have a notion of internal states. So each of these constructs has a semantics given by a stream builder. And we can get the semantics of the entire program by composing these simple stream builders and obtaining a new stream builder. So a stream builder is specified by an initial state, a condition on the initial state that determines the initial value of internal memory streams. So in this case, we don't have any condition on the memory streams. And a set of guarded commands, where each guarded command specifies a possible behavior that the system can perform. And they are exclusive, meaning that only one guarded command can be executed at a given time. And basically, a guarded command is specified as a guard and a command, and the command can be executed whenever the guard is satisfied. So a guard specifies how and when to consume input and memory streams, and an update determines basically assignments and determine how we can write output and memory streams. So we have some predefined constructs for guards, like the get and undefined operator. The get checks if an input or memory stream is defined, in which case consumes the value at the head of the stream. And the undefined checks if a given memory stream is undefined. So here we have the semantics for our alternator. The alternator can either read a value on A and B at the same time, only if the FIFO buffer is empty, and in which case it can buffer the value from B and output the value from A. Or if the FIFO is full, then it can read that value from the buffer and assign it to the output. So these stream builders are based on streams constraints that were previously defined by Docter and Arbab. And the advantage of stream builders and stream constraints is that they don't suffer from the state explosion that comes from an automata semantics. So we said that we have the reactive constructor, the squiggly arrow. So we have to accommodate reactiveness in our stream builders. So here we have a reactive stream builder A being assigned to a stream B, and then B is being outputted. So this is the architectural representation of this program. This means that any value from A is going to be buffered before being sent to B. And this buffering implies that B can always access the latest value read from A. The way we achieve this in our program is by having a new construct, a new guard, ask, which performs non-destructive reads opposite to the get. The semantic of this program is as follows. So either we can read a value on A, consume it, and assign it to a buffer, or if that buffer is defined already, we can read it without consuming that value, and we can output it to B. This value will remain available for B to consult it later. So this buffering of streams might sound similar to the one that we can get from the FIFO construct, where we buffer the values of A before being output to stream B. But there are a few differences. The main one is that in the reactive version, when we buffer a value from A, we can always check for that value as many times as we want, because we perform non-destructive reads. And secondly, we can always buffer a new value of A overwritten a pre-existing value. On the synchronous versions with the FIFO, when we can only buffer a value if there are no previous values. If we want to buffer a new value, we have to consume the old value. And once we have a value, we can consume it only once. So we perform a destructive read. So these are the main difference of buffering a reactive string or a synchronous string. So by introducing these reactive constructs, we provide a reactive semantics for our stream builders. And on a typical reactive programming, the interpretation of this would be that whenever A changes, it's going to trigger an update on B. On our interpretation that we call push-pull interpretation, we give more control to the environment to decide when to read or write values. So in this particular example, B is not only updated when there is an update on A, but it can also be updated whenever A is active, meaning in this case that A was written at least once, and if the environment wants to read B. So this reactive semantics with push-pull interpretation is encoded as an automata for stream builders. And basically, the states of the automatas keep track of the active input, memory, and output streams. And the automata can evolve either by performing some guarded command from the underlying stream builder, or by a change in the context when the system, the environment, decides if it wants to push or pull a value. And initially, there are no active variables, so the only possible way to evolve is by the environment saying that it wants to push or pull a value. So imagine it decides to push a value on A, and we can read that value, buffer it, and produce an update, trigger an update on B. After which, the system can decide to push a new value, overwritten the buffer value, or get an old value of A if it wasn't updated. So it can decide to pull, and then it will read the buffer value, the old buffer value. So in this way, by having this control of push-pull, in this case, particularly the pull, the system can decide to get old values from A in a more continuous way. So to wrap up, we just introduced our toolset for ARCS programs, which merge notions of synchronous and reactive programming. We have a small DSL that has constructs for synchronous and reactive programming. We have notions of algebraic data types. We can analyze these programs and infer, for example, its type and get its semantics based on string builders, which provide a more compact description of the behavior of a program. We also provide reactive semantics for string builders based on an automata, which has a notion of push-pull that gives control to the environment to decide when to read or write reactive strings. Finally, we can also have an architectural view of the program. So now we have time for questions and for some questions. So thank you for listening.